In the winter of 2025, a telescope in Chile captured something that shouldn't exist. An object moving through our solar system from somewhere beyond. Not from the Kuiper belt. Not from the Oort cloud. From outside. From interstellar space. They named it 3I/Atlas. The third confirmed interstellar visitor in human history. But here's what they didn't expect. It wasn't behaving like a visitor. It was behaving like something watching. Now, before you dismiss that statement, understand something important. This isn't speculation from the internet. This isn't conspiracy theory. This isn't science fiction dressed as fact. This is a pattern emerging from data. Raw telescope data, trajectory calculations, spectral analysis, thermal readings, observations from multiple continents, multiple instruments, multiple teams of researchers who have never met each other. Data that astronomers have been quietly studying for months. And the more they study it, the less it resembles anything natural. Think about that for a moment. Every day, new observations come in. Every day, the models are refined. Every day, scientists expect the anomalies to disappear, to resolve into ordinary explanations. But they don't disappear. They multiply. The first interstellar object we detected was Oumuamua in 2017. It was strange. Elongated like a cosmic cigar. No tail despite passing close to the sun. Unusual acceleration that defied simple explanation. Scientists debated for years whether it was a comet, an asteroid, or something else entirely. Some even whispered the word artificial. The second was Borisov in 2019. That one looked normal. A classic comet with a beautiful tail. It behaved exactly as physics predicted. It gave us comfort. It told us that interstellar space sends us ordinary things. That Oumuamua was just a statistical outlier. But 3I/Atlas is neither. It doesn't fit the pattern of Oumuamua. It doesn't fit the pattern of Borisov. It's not creating confusion. It's creating a new pattern entirely. A pattern that some researchers are calling uncomfortable. And that's why we're here tonight. Because by the end of this video, you'll understand exactly what 3I/Atlas is doing. You'll see the 9 documented anomalies that separate it from every natural object we've ever observed. You'll hear the strongest skeptical explanations presented fairly and completely. And you'll understand why those explanations, despite being logical, despite being scientific, keep falling short. This isn't about believing in extraterrestrial intelligence. This is about following the data wherever it leads. Even when it leads somewhere we didn't expect. Even when it leads somewhere that makes us uncomfortable. Even when it leads to questions we don't know how to answer. And right now, the data is leading somewhere unsettling. So stay until the end. Not because I'm asking you to, but because once you see the full picture, once you understand what astronomers are privately discussing, you won't be able to look at the night sky the same way again. The universe just sent us a message. Whether that message is random noise or deliberate signal, we're about to find out. Now prepare yourself. Let the room fall quiet. Let your breathing slow. Let your thoughts settle into stillness. Let the outside world fade away until nothing remains but this moment and these words. We begin part 1 with the moment humanity first realized we were not alone in this solar system. To understand what 3I/Atlas might be, we first need to understand what we know for certain. And what we know begins with a single night in early 2025. The Atlas Survey Telescope, stationed high in the mountains of Chile, was performing its routine scan of the southern sky. This telescope never sleeps. Every clear night, it sweeps across the darkness, searching, cataloging, watching for anything that moves. ATLAS stands for Asteroid Terrestrial Impact Last Alert System. Its job is simple but critical. Find objects that might threaten Earth. Asteroids, comets, anything hurtling toward our planet from the depths of space. On that particular night, it found something moving, but not toward us, through us. The object was faint, almost invisible against the dense background of stars. A tiny smudge of light that most systems would have ignored. But ATLAS doesn't ignore anything. It flags every anomaly, every object that doesn't belong to the fixed pattern of the cosmos. And this object didn't belong. Its motion was unmistakable. It was crossing the sky at an angle that didn't match any known orbit. Not circular, not elliptical, not bound to our sun at all. The astronomers on duty that night ran the preliminary calculations. Then they ran them again. Then they called their colleagues. Within hours, the data was shared with observatories around the world. Hawaii, Arizona, Spain, Australia, South Africa. Telescopes turned toward the coordinates. Cameras opened their shutters. Spectrometers began their analysis. Within days, the preliminary trajectory was complete. This object had not originated in our solar system. Its path traced backward through space and time, pointing to a region far beyond our sun's gravitational influence. It had come from interstellar space, the void between stars, the emptiness that separates solar systems like islands in an infinite ocean. It had traveled across light years, across millions of years, across distances that make human comprehension meaningless. And now, after all that time, all that distance, all that silent drifting through absolute darkness, it was here. The International Astronomical Union moved quickly. They designated it 3I/Atlas. The 3I means third interstellar object ever detected by humanity. The Atlas credits the survey telescope that first spotted it. A historic name for a historic discovery. But a name doesn't explain behavior. And behavior is where this story takes its first unsettling turn. You see, interstellar objects are supposed to follow predictable paths. Physics doesn't negotiate. Gravity doesn't make exceptions. When an object enters a star system from outside, we know exactly what should happen. It falls toward the star. Gravity pulls it faster and faster. It accelerates as it descends into the gravitational well. It reaches maximum speed at its closest approach to the star. Then it swings around and begins climbing back out, decelerating, slowing, fighting against the gravity that tried to capture it. This is called a hyperbolic orbit, a gravitational slingshot, in and out, one pass, never to return. This is basic celestial mechanics. First-year astronomy. This is how every comet and asteroid and rogue planet should behave when passing through a star system. Oumuamua followed this pattern, mostly. Its basic trajectory was hyperbolic, gravitationally predictable. Yes, it had that strange acceleration anomaly near the end of its visit. A tiny push that didn't match any known force. But the overall shape of its path made sense. Borisov followed the pattern almost perfectly. Textbook interstellar comet. It did exactly what physics demanded. Scientists used it to validate their models. 3I/Atlas does not follow this pattern. This trajectory is hyperbolic. Yes, the overall shape is correct. It's not captured. It's not orbiting. It will eventually leave. But the details within that trajectory, the angle of entry, the velocity profile, the response to solar gravity, the subtle variations that should appear in any natural object's path. Each measurement came back slightly off from predictions. Not dramatically off, not science fiction off, not breaking the laws of physics off, just wrong enough to be noticed. wrong enough to require explanation, wrong enough to make researchers run their calculations again and again, checking for errors, checking for instrument problems, checking for software bugs. And every time they ran them, the numbers stayed the same. 3I/Atlas was not behaving exactly like a natural interstellar object should. This is what we call the anchor reality, the foundation of everything that follows, the starting point that no one disputes. An object from interstellar space is passing through our solar system. That much is confirmed beyond any doubt. That much is scientific fact. But what kind of object it is, what it's made of, why it's behaving strangely, and whether passing through is even the right description, that's where certainty ends. And that's where our investigation truly begins. Because there are 9 documented anomalies in the observational data for 3I/Atlas. 9 points where its behavior deviates from expectations. 9 cracks in the comfortable assumption that this is just another piece of interstellar debris. We're going to examine each one, carefully, thoroughly, without sensationalism, without jumping to conclusions. And when we reach the 9th anomaly, you'll understand why some astronomers have stopped calling it an object and started calling it a visitor. But that's not the strangest part. Now prepare yourself for what comes next, because we're about to walk through 9 documented anomalies. 9 observations that don't fit the expected pattern. 9 cracks in the assumption that 3I/Atlas is just another piece of cosmic rock drifting through the void. These aren't theories. These aren't speculation. These are measurements, data points, numbers recorded by instruments that don't have opinions. Telescopes don't lie. Spectrometers don't imagine things. They simply report what they see. And what they're seeing doesn't add up. There are 9 documented anomalies we need to walk through tonight. By the time we finish, you'll understand why this object has generated more private discussion among astronomers than any discovery in decades. Let's begin with the first. Anomaly number 1. The trajectory angle. Every object entering our solar system has an approach angle. Think of it like a highway entrance ramp. You can merge from the left. You can merge from the right. You can come in steep or shallow. The angle is determined by where the object came from, the direction of its origin star, the gravitational influences it encountered during its journey, the random chaos of interstellar space. Natural interstellar objects should arrive from random directions. Space is vast beyond comprehension. Stars are scattered across the galaxy without pattern. There's no reason for incoming objects to favor any particular approach angle. Random means random, but 3I/Atlas arrived at an angle that astronomers call statistically unusual. Its approach vector brings it through the plane of our solar system at an inclination that maximizes observation time from Earth. Not a steep dive that would flash past our telescopes in weeks. Not a shallow pass that would keep it too far from the sun to study properly. But an angle that keeps it visible, trackable, observable for an extended period. An angle that almost seems optimized. Coincidence? Probably. Almost certainly. But noted. Recorded. Added to the file. That detail alone isn't what caught their attention. Anomaly number 2, velocity consistency. When objects fall toward the sun, they accelerate. This is gravity. This is basic physics. This is inescapable. The closer you get to a massive object, the faster you fall. Your speed increases continuously. The acceleration isn't smooth. It varies based on distance, based on the angle of approach, based on 1,000 tiny gravitational influences from planets and moons and asteroids. Natural objects show this variation. Their velocity curves have texture, bumps and dips, subtle fluctuations that reflect the chaotic reality of gravitational interaction. 3I/Atlas is accelerating. It's falling toward the sun. The basic physics is working, but its acceleration curve is smoother than expected. Almost too smooth, as if something is regulating its speed, dampening the variations, filtering out the noise that natural gravitational interaction should produce. The difference is subtle, measured in fractions of meters per second, invisible to casual observation. But the instruments see it. The data shows it, consistent across multiple observations from multiple telescopes on multiple continents. Normal explanation could be measurement error. Every instrument has limits. Could be an unusually uniform density distribution within the object. If the mass is perfectly distributed, the acceleration might appear smoother. What doesn't fit? The consistency itself. Natural objects tumble. They have irregular shapes. They're lumpy and uneven. Their acceleration should show microvariations that reflect their chaotic structure. 3I/Atlas shows almost none, because what happened next doesn't fit any model we have. Anomaly number 3. No outgassing detected. This one is significant. Pay attention. Comets produce outgassing. This is what makes them beautiful. As they approach the sun, solar radiation heats their surface. Frozen compounds begin to sublimate. They transform directly from solid to gas. This releases material into space. Dust and vapor stream away from the nucleus. This creates now prepare yourself for what comes next. Because we're about to walk through 9 documented anomalies. 9 observations that don't fit the expected pattern. 9 cracks in the assumption that 3I/Atlas is just another piece of cosmic rock drifting through the void. These aren't theories. These aren't speculation. These are measurements, data points, numbers recorded by instruments that don't have opinions. Telescopes don't lie. Spectrometers don't imagine things. They simply report what they see. And what they're seeing doesn't add up. There are 9 documented anomalies we need to walk through tonight. By the time we finish, you'll understand why this object has generated more private discussion among astronomers than any discovery in decades. Let's begin with the first. Anomaly number 1. The trajectory angle. Every object entering our solar system has an approach angle. Think of it like a highway entrance ramp. You can merge from the left. You can merge from the right. You can come in steep or shallow. The angle is determined by where the object came from, the direction of its origin star, the gravitational influences it encountered during its journey, the random chaos of interstellar space. Natural interstellar objects should arrive from random directions. Space is vast beyond comprehension. Stars are scattered across the galaxy without pattern. There's no reason for incoming objects to favor any particular approach angle. Random means random, but 3I/Atlas arrived at an angle that astronomers call statistically unusual. Its approach vector brings it through the plane of our solar system at an inclination that maximizes observation time from Earth. Not a steep dive that would flash past our telescopes in weeks. Not a shallow pass that would keep it too far from the sun to study properly. But an angle that keeps it visible, trackable, observable for an extended period. An angle that almost seems optimized. Coincidence? Probably, almost certainly, but noted, recorded, added to the file. That detail alone isn't what caught their attention. Anomaly number 2, velocity consistency. When objects fall toward the sun, they accelerate. This is gravity. This is basic physics. This is inescapable. The closer you get to a massive object, the faster you fall. Your speed increases continuously. The acceleration isn't smooth. It varies based on distance, based on the angle of approach, based on 1,000 tiny gravitational influences from planets and moons and asteroids. Natural objects show this variation. Their velocity curves have texture, bumps and dips, subtle fluctuations that reflect the chaotic reality of gravitational interaction. 3I/Atlas is accelerating. It's falling toward the sun. The basic physics is working, but its acceleration curve is smoother than expected. Almost too smooth, as if something is regulating its speed, dampening the variations, filtering out the noise that natural gravitational interaction should produce. The difference is subtle, measured in fractions of meters per second, invisible to casual observation. But the instruments see it. The data shows it, consistent across multiple observations from multiple telescopes on multiple continents. Normal explanation could be measurement error. Every instrument has limits. Could be an unusually uniform density distribution within the object. If the mass is perfectly distributed, the acceleration might appear smoother. What doesn't fit? The consistency itself. Natural objects tumble. They have irregular shapes. They're lumpy and uneven. Their acceleration should show microvariations that reflect their chaotic structure. 3I/Atlas shows almost none, because what happened next doesn't fit any model we have. Anomaly number 3, no outgassing detected. This one is significant. Pay attention. Comets produce outgassing. This is what makes them beautiful. As they approach the sun, solar radiation heats their surface. Frozen compounds begin to sublimate. They transform directly from solid to gas. This releases material into space. Dust and vapor stream away from the nucleus. This creates the famous coma, the fuzzy halo surrounding a comet's core. This creates the spectacular tail. Millions of kilometers of glowing debris trailing behind like a cosmic wedding veil. Interstellar comets should do the same thing. They've been frozen for millions of years, billions perhaps, drifting through the coldest environment in existence. The space between stars, just a few degrees above absolute zero. When they finally encounter a star's warmth, they should erupt. They should release volatiles. They should announce their presence with light and gas and dust. Borisov did exactly this. The second interstellar object. It had a beautiful coma, a classic tale, textbook cometary behavior. It proved that interstellar comets behave like regular comets when heated. 3I/Atlas has no visible coma. No tal. No detected outgassing whatsoever. It's being heated by our sun. Solar radiation is striking its surface. Energy is being absorbed. The temperature is rising. But nothing is coming out. Silence. One possibility. It's not a comet at all. It's a rocky asteroid. Pure stone and metal with no volatile compounds to release. No ice. No frozen gases. Nothing to sublimate. This explanation works. Many asteroids show no outgassing. But here's where it gets uncomfortable. Anomaly number 4. Spectral silence. When we point spectrometers at objects in space, we read their chemical signatures. This is how we know what distant things are made of. We never touch them. We never sample them. We simply analyze their light. Light reflects off surfaces. Different materials absorb and reflect different wavelengths. Iron absorbs certain frequencies. Silicon reflects others. Carbon has its own signature. Nickel, magnesium, water ice, methane. Every substance leaves a fingerprint in the light it touches. This creates a spectral signature, a chemical barcode, cosmic ID card. Every asteroid we've ever observed has a spectral signature. Without exception. Some are rich in carbon. some in metal, some in silicates, but all of them show something. 3I/Atlas reflects light, but its spectral signature is remarkably flat, almost featureless. The spectrometers see light bouncing off its surface, but that light carries almost no information. No strong absorption lines, no clear emission features. No identifiable chemical fingerprint. It's as if the surface is made of something that doesn't interact with light the way natural materials do. Or as if the surface is designed not to reveal its composition. That word again, designed. It keeps appearing in the margins of research notes, in the private conversations between astronomers, in the questions no one wants to ask publicly, not in published papers. Not yet. The scientific community moves slowly, carefully, skeptically, but the questions are there, hanging in the silence. Let's pause here for a moment. Take a slow breath. Let these 4 anomalies settle. For observations examined. 5 more remain. So far, each anomaly has a possible natural explanation. Trajectory angle could be coincidence. Velocity smoothness could be measurement error. No outgassing could mean rocky composition. Spectral silence could indicate unusual surface material. Each explanation works in isolation. But here's what makes researchers uncomfortable at night. These anomalies are not isolated. They're occurring simultaneously, in the same object. An object that crossed light years to reach us. An object that is only the third of its kind we've ever detected. The probability of one anomaly is acceptable. The probability of 4 anomalies together begins to strain coincidence. And we're not done, because the next 5 anomalies don't make the picture clearer. They make it stranger. Keep that number in mind. It becomes important later. And this is where the data stops behaving like it should. Let's continue our examination. 5 anomalies remain. And these are the ones that have kept astronomers awake. These are the observations that don't just raise questions. They challenge assumptions. They push against the boundaries of what we consider possible. Remember, everything I'm about to share comes from data, telescope readings, instrument measurements, numbers that have been checked and rechecked by teams who desperately want ordinary explanations. They haven't found them yet. Anomaly number 5, the size-to-brightness ratio. Astronomers estimate the size of distant objects by measuring how much light they reflect. This relationship is straightforward. Bigger objects have more surface area. More surface area reflects more light. Simple mathematics. If you know how bright something appears, and you know how far away it is, you can calculate its size. This works for asteroids, for comets, for moons, for dwarf planets, for everything we've ever observed in space. 3I/Atlas appears dimmer than it should. Based on trajectory analysis, based on the gravitational influences we can measure, based on the subtle perturbations in its path, researchers estimate 3I/Atlas is between 100 and 400 meters in diameter. That's significant. That's not a pebble. That's not cosmic dust. That's a substantial object, the size of a sports stadium, perhaps larger, but its brightness tells a different story. The light reflecting from 3I/Atlas suggests something smaller, much smaller, or something that absorbs far more light than any typical asteroid. This mismatch creates a puzzle. First possibility, the size estimates are wrong. Trajectory-based estimation has margins of error. Perhaps 3I/Atlas is smaller than we think. Perhaps our calculations contain mistakes. Second possibility, the object has an unusually low albedo. Albedo measures reflectivity. Fresh snow has high albedo. It reflects most light. Coal has low albedo. It absorbs most light. 3I/Atlas might have a surface darker than almost any known asteroid. A surface that swallows light instead of bouncing it back. Neither explanation is impossible. But consider what we learned from Anomaly 4. Spectral silence. A surface that reveals nothing about its composition. Now add Anomaly 5. A surface that absorbs unusual amounts of light. Pattern emerges. An object that doesn't reveal its composition. An object that doesn't reflect light normally. An object that seems difficult to analyze by design. That word keeps appearing. Design. Scientists resist it. They should resist it. Extraordinary claims require extraordinary evidence. But they notice it. Now watch what happens when we connect these two facts. Anomaly number 6, rotational behavior. Everything in space rotates. Planets spin. Moons spin. Asteroids tumble. This is the legacy of formation. Billions of years ago, when these objects coalesced from dust and gas, angular momentum set them spinning. And in the vacuum of space, nothing stops the rotation. Natural objects tumble chaotically. They spin on multiple axes simultaneously. They wobble and twist and roll. Their irregular shapes catch solar radiation unevenly. This creates torque. This changes their rotation over time. When Oumuamua passed through our solar system, it tumbled dramatically. Its brightness varied wildly as it rotated. Different faces reflected different amounts of light. Scientists mapped its elongated cigar shape by studying these brightness variations. 3I/Atlas shows minimal brightness variation, almost stable, as if it's rotating on a single controlled axis, or as if it's not tumbling at all, as if something is maintaining its orientation, keeping it steady, holding it stable against the chaotic forces that should set it spinning randomly. Stable rotation in space requires one of two things: perfect spherical symmetry, a shape so uniform that no force can create torque. Natural asteroids are not spheres. They're lumpy, irregular, potato-shaped chaos, or stabilization, active or passive systems that maintain orientation. Gyroscopes, reaction wheels, spin-stabilized design. That explanation works until you see the next anomaly. Anomaly number 7, course timing. This anomaly is different. It's not about physics. It's about probability. It's about asking uncomfortable questions regarding coincidence. 3I/Atlas is arriving now. Not a million years ago when dinosaurs ruled Earth. Not a million years from now when humanity might be extinct. Now, in this specific decade, in this narrow window of human history, consider what this moment represents. Humans have had telescopes for roughly 400 years. Galileo first pointed glass lenses at the sky in 1609. For most of those 4 centuries, our instruments were primitive. We could see planets, bright comets, nearby stars, but small interstellar objects passing through our solar system. Invisible. Only in the last decade have we developed the sensitivity to detect these visitors. Advanced CCD cameras, automated survey telescopes, software that can identify tiny moving objects against the background stars. Only now can we see what has always been passing through. And in this precise moment, when humanity finally develops interstellar detection capability, the third interstellar object arrives. On a trajectory that maximizes our observation time. The timing is noted. Probably coincidence. Almost certainly coincidence. But noted. Anomaly number 8. Non-responsive to solar wind. The sun doesn't just emit light. It emits particles. A constant stream of charged matter flowing outward in all directions. Protons, electrons, ions. This is called solar wind. Solar wind pushes against everything in the solar system. Small objects get pushed more. Large objects get pushed less. Light sails use this principle for propulsion. Every object we've observed responds to solar wind. The response is tiny, microscopic, but measurable with precise instruments. 3I/Atlas shows no measurable deflection from solar wind. None. This could mean it's extraordinarily dense, more massive than its size suggests, packed with heavy elements. Or it could mean our measurements aren't precise enough yet. But combined with anomaly 5, another contradiction emerges. The size-to-brightness ratio suggests it might be smaller than trajectory analysis indicates. The solar wind response suggests it might be more massive than size estimates allow. The data doesn't converge. The numbers don't agree. Different measurements point in different directions, as if the object is deliberately confusing our analysis. And no one has been able to explain why. Anomaly number 9. The approach angle revisited. We discussed trajectory in anomaly 1, but there's a deeper layer we haven't explored. 3I/Atlas will pass within observable range of Earth at a distance that is remarkably convenient. Close enough to study in detail. Our telescopes can resolve meaningful data. Our spectrometers can attempt analysis. Our instruments can gather information, but far enough to pose no threat, no collision risk.
No gravitational disruption. No danger.
Not a threatening approach. Not a distant flyby we'd barely notice. An optimal observation distance. As if it wants to be seen. As if it's presenting itself for examination while maintaining safe distance. As if it's checking. That was anomaly number 9. 9 cracks in the assumption of ordinary. 9 questions without comfortable answers. By late 2026, 3I/Atlas will reach its closest approach. And when it does, we'll finally know if it behaves like rock or something else entirely. But before we explore what else it might be, we need to hear the strongest case against everything I've just told you. We need to hear what the skeptics say. This is the part that made astronomers go quiet. Let's stop here. Take a slow breath. Let the anomalies settle into your mind. Let the questions find their resting place. Because everything we've discussed so far has an alternative explanation. A mundane explanation. A scientific explanation that requires nothing extraordinary. Nothing unprecedented. Nothing that would rewrite our understanding of the universe. And if we're being intellectually honest, that explanation is probably correct. The universe is vast. The cosmos is ancient. Strange things happen. Unlikely combinations occur. Statistical outliers exist. So let's build the skeptic's best case. Let's construct the strongest possible argument against everything we've examined. Let's give the ordinary explanation its full voice. Because if we're going to consider extraordinary possibilities, we first need to understand why most scientists reject them. The case for ordinary. Interstellar space is not empty. We imagine the void between stars as pure nothingness. Black vacuum stretching for light years.
Absolute absence.
But this isn't accurate. Interstellar space is filled with debris. Trillions upon trillions of objects drifting in the darkness. Asteroids ejected from forming solar systems. Comets thrown outward by gravitational chaos. Fragments of planets torn apart by stellar encounters. Rocks and ice and dust expelled from a billion different origins. The galaxy is littered with wanderers. Most are small, invisible, undetectable with current technology. They pass through solar systems constantly. They've been passing through our solar system for billions of years. We simply couldn't see them before. Now we can. And we're surprised by what we find. But should we be surprised? When you have trillions of samples, statistical outliers become inevitable. Not possible. Inevitable. Some objects will have unusual trajectories, pure chance, random angles from random origins. A few will happen to match observation-friendly paths. Some will have flat spectra,
Unusual surface composition.
materials we haven't cataloged yet. Some will have low albedos, dark surfaces that absorb light, processed by cosmic radiation over millions of years. Some will show stable rotation, lucky geometry, symmetric mass distribution by accident. When you roll enough dice, you eventually roll unusual combinations. 3I/Atlas might simply be one of those statistical outliers. Rare, unusual, unexpected, but not impossible. Not even improbable given the scale of the cosmos. The case for measurement error. Our instruments are powerful. Modern telescopes can detect objects billions of light-years away. Spectrometers can identify elements in distant stars. Our technology is remarkable, but no instrument is perfect. Every measurement has error bars. Every observation has uncertainty. Every data point exists within a range of possible values. 3I/Atlas is far away. It's small. It's faint. It's moving. It's difficult to observe. Every measurement we take pushes our instruments to their limits. Every data point carries significant uncertainty. The anomalies we've discussed exist within those margins. Velocity smoothness could be instrument noise averaging out natural variations. Spectral silence could be low signal-to-noise ratio obscuring real chemical signatures. Size-brightness mismatch could be estimation errors compounding across multiple calculations. When data is uncertain, patterns can appear where none exist. Our brains are pattern recognition machines. We evolved to find connections, to see faces in clouds, to hear voices in static, to impose order on chaos. This is called apophenia, the tendency to perceive meaningful patterns in random information. Scientists guard against apophenia constantly. They use statistics, double-blind studies, peer review, repeated observations. They build systems specifically designed to filter out false patterns. But the temptation remains, especially when the pattern is exciting, especially when it suggests something profound. 3I/Atlas might be triggering our pattern recognition instincts without justification. We might be seeing design where only randomness exists. This explanation deserves serious consideration. The case for unknown natural phenomena. Here's something important to remember. We've only detected 3 interstellar objects. 3. Oumuamua, Borisov, 3I/Atlas. That's our entire sample size. 3 data points. 3 examples from which to draw conclusions about what interstellar objects should look like. That's not enough. We don't actually know what's normal for interstellar objects. We've assumed they should behave like local comets and asteroids. But why should they? They formed in different star systems, under different conditions, around different types of stars, in different galactic environments. Maybe interstellar objects are commonly strange. Maybe the space between stars processes materials in ways we don't understand. Cosmic radiation bombardment for millions of years. Magnetic field interactions over vast distances. Temperature extremes beyond anything in our solar system. Timescales that dwarf human comprehension. 3I/Atlas could be made of materials we haven't encountered in our solar system, structured by processes we haven't studied, shaped by an environment we've never directly observed. Unknown doesn't mean artificial. Unknown simply means unknown. We should be humble about our ignorance. The strongest skeptical argument. Here it is. The single most powerful reason to believe 3I/Atlas is natural. We have no evidence of extraterrestrial intelligence anywhere. None. 0. In decades of searching, we've found nothing. Radio telescopes have scanned the skies for artificial signals. Nothing. Optical telescopes have searched for laser pulses. Nothing. Surveys have looked for megastructures around distant stars. Nothing. Atmospheric analysis has sought biosignatures on exoplanets. Nothing conclusive. The universe appears empty, silent, devoid of intelligence except for one small planet orbiting an ordinary star in an unremarkable galaxy. If intelligent life existed elsewhere, if it had achieved interstellar travel capability, if it was sending probes to other star systems, we should see evidence everywhere. The galaxy is old, billions of years old. Plenty of time for intelligence to arise. Plenty of time for civilizations to spread. Plenty of time for probes to reach every corner of every solar system. Where is everyone? This is the Fermi paradox. The contradiction between the high probability of extraterrestrial civilization and the complete absence of evidence. Its weight presses against every claim of artificial origin. 3I/Atlas is probably natural because everything else appears natural. Because we've never found anything artificial. Because the extraordinary claim requires extraordinary evidence. And we don't have that evidence. Not yet. The skeptical case is strong. It's rational. It's scientific. It's intellectually rigorous. It's probably right. I want you to sit with that, to feel its weight, to understand that the simplest explanation is almost always the correct one. But there's a problem, a crack in the skeptic's armor. The skeptical case explains each anomaly individually. It provides a separate explanation for each strange observation. Trajectory angle, coincidence, velocity smoothness, measurement error,
No outgassing. Rocky composition.
spectral silence, unusual surface material, size brightness mismatch, estimation uncertainty, stable rotation, lucky geometry, course timing, pure chance, solar wind response, high density, optimal observation distance, random probability, 9 anomalies, 9 separate explanations. Each explanation is plausible in isolation. But what the skeptical case doesn't address, what it cannot easily dismiss, is why all 9 anomalies appear in the same object. The probability of one anomaly is acceptable. The probability of 2 anomalies together is lower. 3 is lower still. 4, 5, 6, 7, 8, 9. Each additional anomaly multiplies the improbability. Each additional coincidence strains the statistical argument. At what point does coincidence become pattern? At what point does ordinary become inadequate? At what point do we have to consider, even if we don't want to, even if it frightens us, even if it changes everything, the uncomfortable alternative? The question isn't what 3I/Atlas is. The question is what it's doing. And that question remains open. Now we enter difficult territory. Let your mind open. Let your assumptions loosen. Let yourself consider possibilities that exist beyond the comfortable boundaries of established science. Everything that follows is hypothesis, speculation, possibility, not fact. Not proven, not claimed as truth, but considered, because the data allows it, because intellectual honesty demands we examine all explanations, not just the ones that let us sleep peacefully. We're going to build what scientists call a speculation ladder. 3 hypotheses, 3 possible explanations for what 3I/Atlas might represent, each one stranger than the last. Each one further from ordinary. You don't have to believe any of them, but you should understand them. Hypothesis A, the natural outlier. This is the most conservative interpretation, the one that requires the least adjustment to our current understanding of the universe. 3I/Atlas is a genuine interstellar object, natural in origin, ancient beyond comprehension, formed billions of years ago in a distant star system we'll never identify. Picture its birth. A young star surrounded by swirling gas and dust, planets coalescing from the chaos, asteroids and comets forming in the outer regions, gravitational forces pulling and pushing, orbital dynamics playing out over millions of years, and then ejection, a close encounter with a giant planet, a gravitational slingshot that flung this object outward, beyond its home system, beyond its parent star's influence, into the void. For billions of years it drifted, through absolute darkness, through absolute cold, through absolute silence, until finally, by pure cosmic coincidence, it entered our solar system. Its anomalies are statistical noise, rare combinations of ordinary properties, like shuffling a deck of cards and dealing a royal flush. Unlikely, remarkable, but not impossible. This hypothesis requires no new physics, no intelligence, no design, no purpose, just probability doing what probability sometimes does. Most scientists hold this position. They hold it because it's conservative, because it doesn't require extraordinary assumptions, because Occam's razor favors the simplest explanation. And they're probably right, probably. But probably isn't certainly. And science doesn't advance by ignoring possibilities. It advances by examining them. Hypothesis B, the artifact. This interpretation steps further into uncertainty. What if 3I/Atlas is artificial, but not active, not a functioning probe, not a deliberate visitor, not a conscious observer, just debris, a relic from a civilization that existed millions of years ago, perhaps billions, a civilization that rose and fell while our sun was still young, a civilization that launched objects into interstellar space and then vanished, extinct, forgotten, lost to time. Their technology remains, drifting, tumbling through the galaxy, passing through solar systems without purpose, without mission, without anyone left to care. Think about what humanity has already launched into interstellar space. Voyager 1 and Voyager 2, Pioneer 10 and Pioneer 11. New Horizons eventually. These spacecraft will drift for millions of years. Billions perhaps. Long after humanity is gone. They'll still be out there. Silent, dead, carrying records of a species that no longer exists. If other civilizations existed, if they launched their own probes, the galaxy could be littered with artifacts, ancient machines on endless journeys to nowhere. 3I/Atlas could be one of them. This would explain several anomalies. The spectral silence. Artificial materials might not match natural chemical signatures. Alloys and composites designed for specific purposes rather than formed by geological processes. The stable rotation. Manufactured objects could be deliberately symmetrical, designed for stability, built to maintain orientation over vast timescales. The low albedo, a surface designed to absorb radiation for power generation. Solar panels darkened by millions of years of cosmic ray bombardment. But Hypothesis B raises questions it cannot answer. Where is the civilization that built it? What happened to them? Why did they launch it? Did they know it would eventually reach us? Did they care? Hypothesis B gives us an artifact without an owner, a message without a sender, a mystery without resolution. It satisfies curiosity while creating deeper uncertainty. But there's one more possibility, one more rung on the speculation ladder. And this is the one no one wants to say out loud. Hypothesis C, the observer. What if 3I/Atlas is not debris, not dead, not abandoned, What if it's active? What if its trajectory is not coincidental? What if its timing is not random? What if its optimal observation distance is not luck? What if it came here specifically to observe, not to invade, not to conquer, not to make dramatic contact with lights in the sky and messages of peace, just to watch, to measure, to catalog, to collect data on a developing civilization, to assess our technology, our capabilities, our potential, to check. Consider this from their perspective. If you wanted to study a primitive civilization without interfering with its development, how would you do it? You wouldn't send obvious spacecraft covered in lights and signals. That would contaminate your observations. That would change the very thing you're trying to study. You would send something subtle, something that looks natural, something that could pass through their solar system without triggering alarm, something that appears to be an interstellar rock. You would design it to resist analysis, flat spectra, low albedo, materials that don't reveal their composition. You would give it a trajectory that maximizes observation time while maintaining safe distance. Close enough to gather detailed data, far enough to avoid provoking response. You would time its arrival carefully. When the civilization has developed enough technology to detect interstellar objects, but not enough to intercept them. Now, this moment, this decade, under Hypothesis C, every anomaly becomes a feature rather than a bug. The unusual trajectory angle, designed for maximum observation coverage. The velocity consistency, controlled approach speed to optimize data collection. The spectral silence, deliberate concealment of artificial composition. The stable rotation, sensor platform stability for sustained observation. The optimal distance, close enough to watch, far enough to remain safe. Under this hypothesis, 3I/Atlas is not passing by. It's performing reconnaissance. And we are the subject. Now let's be absolutely clear. Hypothesis C is the least likely, by far. It requires the existence of extraterrestrial intelligence. It requires that intelligence to have developed interstellar travel. It requires them to have interest in us specifically. Each requirement multiplies the improbability. Each assumption strains credulity. But here's what keeps researchers uncomfortable. Hypothesis C is the only interpretation that explains all 9 anomalies with a single coherent explanation. Not 9 separate coincidences requiring 9 separate justifications. One intention, one purpose, one design. The skeptical mind rejects this, as it should. Extraordinary claims require extraordinary evidence. But the curious mind notes it, files it away, waits for more data. In early 2027, the James Webb Space Telescope is scheduled for direct observation of 3I/Atlas. That data will either close this case forever or open something we're not prepared for. The universe keeps its secrets carefully, but sometimes it offers hints. Whether we're ready to receive them is another question entirely. So where do we go from here? The questions have been raised. The anomalies have been documented. The hypotheses have been constructed. But questions without answers are just noise. Speculation without resolution is just entertainment. Science demands more. Science demands testable predictions, observable checkpoints, moments when theories succeed or fail based on evidence. And those moments are coming. 3I/Atlas is still moving, still approaching, still presenting itself for observation. The next few years will provide data that could settle this debate forever, or deepen the mystery beyond anything we've imagined. Let me walk you through what happens next. The specific events, the precise checkpoints, the moments when our understanding will either solidify into comfortable certainty or shatter into terrifying possibility. Checkpoint 1. Perihelion, late 2026. Every object passing through our solar system has a perihelion, the point of closest approach to the sun, the moment of maximum solar heating, the instant of peak gravitational stress. For 3I/Atlas, that moment comes in late 2026. As it rounds the sun, solar radiation will intensify. The surface temperature will rise dramatically. Whatever materials comprise its outer shell will experience thermal stress they haven't felt in millions of years. If 3I/Atlas is a natural comet with buried volatiles, perihelion should trigger outgassing. Even deeply buried ice will sublimate under intense solar heating. Gas will escape. Dust will follow. Coma should form. Tail should develop. The object should announce its cometary nature in the most visible way possible. This is what happened with Borisov. As it approached the sun, it behaved like a comet should. If 3I/Atlas reaches perihelion and still shows no outgassing, the silence becomes harder to explain. Not impossible to explain. Rocky asteroids don't outgas. But harder, the spectral silence, the compositional mystery, the stubborn refusal to reveal its nature. All of it would deepen. Watch for reports in late 2026. Astronomers worldwide will be observing. The data will be published. The results will be discussed. And we'll know something we don't know now. Checkpoint 2. Direct imaging, early 2027. The James Webb Space Telescope represents humanity's most powerful eye in the sky. Its infrared sensors can detect heat signatures across unimaginable distances. Its resolution exceeds anything we've previously deployed. Its spectrometers can analyze light with precision that would have seemed magical a generation ago. JWST has already transformed our understanding of distant galaxies, of exoplanet atmospheres, of the early universe. Now it may transform our understanding of 3I/Atlas. Observation requests are already being submitted. Astronomers are preparing proposals. The scientific community recognizes the significance of this target. If JWST observes 3I/Atlas directly, we'll learn things our current instruments cannot tell us. Surface temperature distribution, hot spots and cold spots, thermal patterns that might reveal internal structure. Detailed spectral analysis at wavelengths our ground-based instruments cannot access. Possible compositional signatures hidden from current observation. Albedo measurements across multiple infrared wavelengths. A more complete picture of how the surface interacts with electromagnetic radiation. The data from JWST could confirm natural origin beyond reasonable doubt. Or it could reveal anomalies we haven't even imagined yet. In early 2027, those observations should occur. The analysis will take time. Peer review will take longer. But eventually, the results will become public. And everything might change. Checkpoint 3. Trajectory refinement ongoing. As 3I/Atlas continues its journey through our solar system, our trajectory calculations become more precise. More observations mean more data points. More data points mean smaller error bars. Smaller error bars mean greater confidence in our predictions. Right now, our trajectory models have uncertainty. Margins where natural variation might hide. Gaps where anomalies might be measurement artifacts rather than real phenomena. Those gaps are closing. Every week brings new observations. Every month refines our understanding of exactly where 3I/Atlas is and exactly where it's going. If its path shows any deviation from gravitational prediction, any acceleration or deceleration that cannot be explained by known forces, that would be significant. Oumuamua showed anomalous acceleration. A tiny push as it departed our solar system. Scientists attributed it to outgassing we couldn't directly detect. Invisible jets of gas providing thrust. But some researchers questioned that explanation. Some noted that no outgassing was ever observed. Some wondered if the acceleration had a different source entirely. The debate continues to this day. If 3I/Atlas shows similar anomalies, the debate will intensify exponentially. Because now we have context. Now we have pattern. Now we have two interstellar objects behaving in unexpected ways. Once is an anomaly. Twice is a coincidence. 3 times is a pattern. Watch for trajectory updates. They'll be published in astronomical journals, discussed at conferences, debated online. The numbers will tell a story. Checkpoint 4. The departure, 2028 and beyond. By 2028, 3I/Atlas will begin its exit from our solar system. It will climb away from the sun, decelerating as gravity tries to pull it back, fading from our telescopes as distance increases, eventually passing beyond our ability to observe with current technology. But the departure trajectory matters enormously. If 3I/Atlas exits on a path that mirrors its entry, gravitationally symmetric, that strongly suggests natural ballistic motion, an object thrown through space by physics alone.
No guidance. No intention. No adjustment.
This is what we expect. This is what should happen. But if the exit path differs from prediction, if there's any course correction, any subtle adjustment that cannot be explained by gravity alone, that would tell us more than everything else combined. Because natural objects don't adjust course. Rocks don't navigate. Debris doesn't correct trajectory. Only design systems do that. Only machines with purpose. Only vehicles with destination. By 2028, it will begin its exit from our solar system. And if the pattern changes during departure, that will tell us more than anything we've measured so far. What you should watch for. In the coming months and years, pay attention. Not to speculation, not to theories, not to dramatic claims from unreliable sources. Pay attention to data. Look for these specific reports from credible astronomical sources. Outgassing detection results from perihelion observations. JWST spectral analysis findings. Trajectory refinement updates from major observatories. Unexpected acceleration or deceleration measurements. Departure vector calculations and predictions. Each report will either confirm the natural hypothesis or deepen the mystery. The scientific process is slow. Frustratingly slow sometimes. Peer review takes months. Publication takes longer. Verification requires repeated observation. But the answers are coming. Slowly, carefully, methodically. The universe doesn't rush for our curiosity. But it does eventually reveal its secrets to those patient enough to watch. And 3I/Atlas, whether ancient rock or abandoned relic or active observer, has given us a reason to watch more carefully than ever before. The next 3 years will determine which hypothesis survives. The next 3 years will either close this mystery or open something far larger. The waiting begins now, but we're not done. Because there's one more thing to consider. One final perspective before sleep claims you. Now let your thoughts slow down. Let the data fade into the background. Let the anomalies settle into silence. Let the hypotheses rest without demanding resolution. Because regardless of what 3I/Atlas truly is, regardless of whether it's ancient rock or forgotten artifact or conscious observer, its presence in our solar system teaches us something profound, something that transcends the mystery itself. We are not isolated. For most of human history, we looked at the stars and saw only distance, incomprehensible distance, light years of emptiness stretching between points of light. A cosmos so vast that connection seemed impossible. So far that nothing from out there could ever touch us here. We were alone on our small blue world, surrounded by void, separated from everything else by gulfs of space and time that made the universe feel like a painting rather than a place. Beautiful to observe, impossible to reach. But interstellar objects change that understanding. They prove something we always suspected but couldn't confirm. Material crosses between star systems. What happens around distant suns doesn't stay there forever. The galaxy is not a collection of isolated islands. It's an ocean with currents. Things drift from shore to shore, and sometimes they drift to us. 3I/Atlas traveled for millions of years to reach this moment. Perhaps billions. Think about that timescale. Let it sink into your comprehension. Millions of years. When 3I/Atlas was ejected from its home system, humans didn't exist. Mammals didn't exist. Complex life on Earth was just beginning its slow experimentation. Continents had different shapes, different positions. The Earth itself was a different world. And this object, this silent traveler, was already on its way, drifting through absolute darkness, through temperatures just above absolute zero, through emptiness so complete that no human mind can truly grasp it. No sound, no light,
No worms. No companion.
just motion, just patience, just the slow progression of physics unfolding over timescales that make our entire civilization look like a lightning flash. And now it's here, passing through the same solar system where you exist, where you breathe, where you wonder, where you lie in the darkness listening to these words. The same sun that warms your face is warming its ancient surface. The same gravity that holds you to Earth is bending its path. For this brief moment, measured in months rather than millions of years, you share space with a traveler from the stars. Whether natural or artificial, that journey commands respect. That persistence deserves acknowledgement. That arrival merits wonder. If 3I/Atlas is simply rock, it's still extraordinary. A messenger from the deep past. A fragment of a solar system that formed when our sun was still a collapsing cloud of hydrogen. A time capsule carrying information about conditions and processes that predate everything we know. Every atom in its structure was forged in a different star. Every molecule was assembled under different conditions. Every crystal formed in an environment we've never directly observed. Carries the signature of elsewhere. And that alone makes it precious beyond measure. If it's something more, if hypothesis B or hypothesis C contains truth we're not ready to accept, then we are witnessing a moment that science fiction has imagined for a century. First contact. Not the dramatic version. Not radio signals decoded into mathematical messages. Not spacecraft landing on the White House lawn. Not alien ambassadors delivering greetings and warnings. Something subtler. Something quieter. Something that could pass unnoticed if we weren't paying attention. A silent visitor that asks nothing and says nothing and simply observes. Records. Notes. Continues on its way. Either answer is humbling. Either answer reminds us how small we are. How brief our existence has been. How much we have yet to learn. How much the universe contains that we've never touched. So tonight, as sleep approaches, as your thoughts grow soft and your awareness fades, consider this. Right now, at this very moment, 3I/Atlas is out there, moving through the darkness, following its ancient trajectory, reflecting the faint light of our sun. Carrying its secrets through the void. It doesn't know you're thinking about it. Or maybe it does. That uncertainty is part of the wonder. And we are watching it. Telescopes across the planet. Sensors gathering photons. Computers processing data. Scientists puzzling over anomalies. Just as Perhaps it is watching us. Two observers, separated by millions of kilometers of vacuum, each studying the other, each wondering, each waiting to see what happens next. That connection, however uncertain, however tenuous, is something new in human history. We have never had a visitor like this before. We have never had a reason to wonder like this before. Now we do. And that wondering, that beautiful uncertainty, is a gift, not a burden, not a source of fear. A gift, because wonder is what drives us forward. Wonder is what built the telescopes. Wonder is what sent the probes. Wonder is what keeps us looking up when we could so easily look down. 3i/Atlas has given us fresh wonder. That alone makes its visit worthwhile. Whatever it is, whatever it's doing, whatever it knows or doesn't know about us, let that wonder stay with you. Let it settle into your dreams. Let it color your sleep with the vastness of the cosmos. And when you wake, when sunlight returns and ordinary life resumes, take a moment. Look up. Remember that the sky is not empty. Remember that visitors come from distances we can barely imagine. Remember that the universe is stranger and more alive than we ever suspected. Remember that you exist in a moment when humanity can finally see what has always been passing through. 3i/Atlas will continue its journey. Through our solar system, past our sun, back into the void, onward to wherever physics or purpose takes it next. And we will continue ours, building, learning, wondering, reaching. Someday, perhaps we'll send our own visitors to distant stars. Someday, perhaps another civilization will puzzle over our silent travelers. Someday, perhaps, the questions raised tonight will have answers. Until then, we watch, we wait, we wonder, and we sleep beneath stars that have never seemed quite so close. Rest now. The universe is keeping its vigil, and so are we. Good night.